So we're here to talk about parsnip. There's the hex sticker, of course. That's the first thing we did. So I've talked about this, and you're probably sick of seeing this, but there's a bunch of things. The unofficial, like Jay didn't say this, but the unofficial job that I have at RStudio and others do is to these are my words, make R suck less, right? So the things that we don't like about R that sometimes are frustrating, that's what a lot of the tidyverse does. And since I mostly work on modeling, you can see the sort of indictments here of the parts of modeling in R that are a little bit painful if you do it. There's things like, some models have a formula method or a non-formula method. Packages, you don't necessarily know which one is which, or they're going to have, which one they don't have. There's things like, the one that's been frustrating for me for a long time is models, when you build a model and then you go to make predictions and they forget that the data frame you're using has some missing values in it. And so let's say you have 100 rows and 2 missing values. And so most of the predict methods, you get 98 things back, right? And then you're oh, well, yeah, how do I put that back? How do I unbreak this egg? And so, there's just various things for a long time that have been building up. Because, before joining RStudio, I used to do modeling for a living. So, so there's lists there of things that are just a little bit frustrating. And then, the table on the side is more the table I've been talking about with Carrot about. There's the APIs with packages can be so different. It can be really frustrating having to remember all of that. So you've probably heard that before from me. So, I wrote Carrot in 2005, and Carrot does a variety of different things. But one of the things it does is it works on solidifying a simple API that you can use and let the R package figure out, well, what does that mean for XGBoost, or what does that mean for LM, and so on. And so, and that works pretty well, but with the tidymodels packages we're developing, we want to, we've gotten, or at least I've gotten, I think, better at APIs. I never really thought about it. And when you work for somebody, Hadley, who, that's his main thing is let's write better APIs, then, we think there's maybe a better way of doing this. And so what parsnip is, it's only the part of Carrot that's designed, similar to the part of Carrot that's designed to solidify a single API that you can work on and not have to worry about what the underlying model function or package requires you to do. So that's all that it is. So one thing we do differently in parsnip is we organize around model type, right? So if you're fitting a linear regression, right, slopes and intercepts, that's a pretty common structure for a model, or if you're fitting a decision tree. So when we talk about, as you'll see in a minute, when we set up a model, you start off with what kind of model do you want to use? And then after that, you specify, well, what's the computational engine? And that's kind of a mashup of the actual implementation or the estimation method, right? So Stan might be a computational engine, which if you're fitting a linear regression model, it's not only a different package, but it's a whole different estimation procedure than, let's say, LM or GLIMNet and things like that. So the idea is you specify the type of model that you want, and then you specify how/where do I estimate that with. So that's how it generalizes things. It has a tidy interface, so you can imagine there's a lot of pipes involved. And then the thing that is we worked on the most, I think, is having a predictable object come back. So whether you're predicting or getting a model object, you always should know with parsnip what you're getting. And I'll talk about that in a minute or two. We spent a lot of time in talking to people and formulating things. There's a link there where we wrote some guidelines for what we think models should do. Just not specifications, but things with predict, always return the same number of rows that you were given, right? And that's, so we're trying to, going forward, trying to solve the problem of, people who aren't software engineers who haven't been using R for a while. They might have an awesome modeling method, but they don't really know anything about making R packages, especially ones for models. And so these guidelines and some of the packages we're developing are set up so that you just drop in your computational algorithm that you're really, really good at and let us work out the whole interface stuff, because that's kind of what we do. So parsnip is the first step in that direction. There's 2 blog posts that are linked there. One was when I first launched it, and the other I wrote last week. And then I wrote it a few months ago, and then finally I was oh, right, I need to make this public. And I forgot I had written a line that people tweeted about. It's if you look at how parsnip works, quote, you might question our sanity. But so that second blog post is really about this is why, because I rewrote this thing 4 times, why we did it the way we did it. So if you're a glutton for punishment, go ahead and check that out. So just some code. We have a sort of a meta package called tidymodels that loads parsnip and RSample and recipes and all that stuff. And so you can see where we create that first regression model object. All we're saying is, hey, we're going to do linear regression, and there's some common parameters that you might fit in various linear regression models. So if you were doing some sort of regularized model like GlimNet or ridge regression or lasso or something like that, we sort of abstract out the arguments too. So GlimNet might use lambda and another package might use this. We try to come up with a standardized set of non-jargony argument names. So lambda doesn't really tell you much unless you read the papers involving this stuff. So we use words like penalty and so on, just to standardize that. So you would specify what model you want to use and any arguments that you know about that you want to fix. And then at that point, you really haven't done anything. There's no data involved there. So it's just like a specification, right? And so once you have the specification, you can set the engine. And the engine, again, could be whatever we have implemented for that type of model, but it's, in this case, let's say GlimNet, since we have that penalty parameter there. So you never really have to use this translate function that's on the right, but just to give you an idea what happens is, and again, I haven't shown you any, or I haven't shown the code any data yet, but it does a translation. It says, okay, when we fit the GlimNet model, we're going to have X is going to be wrapped in, it's called missing arg because we haven't specified any data there. But you can see for linear regression, it fills in the family should be Gaussian. It translates penalty to lambda and so on. So again, much like Caret, it's doing the whole translation to what GlimNet wants, or Stan or LM or whatnot for you, and you don't have to really worry about the details. So again, like GlimNet, it's a great model, but I'm frequently confounded by that package. And like one of the simplest things that I could point out is the interface of GlimNet is it always requires a matrix for your predictors, not like a data frame. It doesn't take the formula method. So again, like I've made this joke in the workshop the other day. Like sometimes when I'm using XGBoost or GlimNet, the question I'm doing different things for those packages, and I ask myself like, is GlimNet working for me or am I working for GlimNet, right? And so we want to get you all away from that. So for example, once you set the engine and the model type, then you can run a fit function on that. So if you just use fit, you can give it a formula, and whether the underlying model takes a formula or not, it just makes that all happen. Or you could do fit underbar xy and give it xy even if it takes a formula. So you don't have to really worry about like how does the data get there, just give it the data that you think it should get in the format that you want it in, or the format at least maybe you have it in, and so on. So that's sort of how it works in a really simple way. And you can see those two model results are the same despite how we specified the predictors and all that. So Jared kind of stole my slide the other day. I mean, I appreciate it, but I had a slide where I fit the empty cars, like Stan and LM, and I was like, damn it. So what I did is, just as a different example, you can set up a boosted tree. In this case, it would be a regression tree. I'm sorry, classification tree because it's iris. And the arguments I used were trees and min n. And so those get translated to the appropriate arguments in XGBoost, or in this case, C5. Right? So it would be legit for you to be like, oh, well, yeah, all these packages have different arguments. Now you're giving me like another set of arguments to memorize. And that's not false, but hopefully this will be like the last set of arguments you'll have to memorize for what those functions do. And you can see the output's kind of messy for what those packages give you, but like if you look at on the left, you can see that it translates the argument for trees into what XGBoost uses, which is n rounds. And then, you can see it on the right-hand side. C50 calls it trials. So again, you don't have to memorize any of that stuff. You just memorize the top level sort of functions. The other notable thing about this is you might notice if you use recipes or dplyr, we're very much exploiting the idea of like delayed execution, right? So most fitting functions, when you give them a formula and things like that, they automatically instantly evaluate all the arguments. And so what we're doing a lot in the tidyverse is we're saying, well, what can we buy ourselves if we don't immediately evaluate those things? We store them as expressions in their environments. Can we do things we couldn't have normally done by not just immediately eagerly executing and evaluating those arguments? That's a lot of what's going on under the hood. All right, so predictions. Like, this was italicized, I'm like, bold it. It will always give you the same number of things that you came in with. You start off with 100 rows in your data frame, you get 100 predictions back. Now, it's a tidyverse, right? So we're not going to give you a vector back. So, we've standardized and documented, you're always going to get the right or the same format back. So if you're making predictions on a regression model, like a univariate regression model, you'll always get a tibble back with a column name called .pred, right? So in case you have a predictor in your data set called pred, like don't do that, but just in case you go to cbind these things in together, you don't have to worry about name conflicts. So we dot everything, which is not uncommon in a lot of what we do. You can see there, I take the first 30 data points and then predict on the remaining 3, and you see we get 3 rows back. So let's maybe induce a missing value, and then you can see that when you run the predict method, you get a missing value back in the first one, so you can still cbind these things in together. So for our predict method for parsnip, there's no real NA action dot whatever. We give you what you started off with, which is good. Now, if you've used GlimNet, you might realize that the prediction method is actually more complex than that. So the way GlimNet works is GlimNet fits basically a series of penalty parameters when it does this regularized regression. And you don't actually need to say what the penalty is until you go to make predictions. So the cool thing about that is when you're doing model tuning, if you're evaluating that model over many different values of the penalty, you don't have to refit that model over and over again. You can fit one model and then get predictions on all the submodels you might want to evaluate. And so we wanted to facilitate that in parsnip like we do in Caret and other places. Now, we went back and forth about this so much. How do we do that in the predict method? And we figured out that making the predict method work with those particular types of models was going to make it difficult for all the other types of models that don't use that feature. So then the answer we came up with is have something called multi-predict method, which is saying that I'm going to get multiple submodels back. Okay, so you would use, when you want to be in that mode, use a separate prediction method on that same object to get many different predictions from many different models. But I did say that we will always give you a tibble back with the same number of rows that you started out with. So if I go to make a prediction on 30 empty cars and I have 32 data points, I should get 32 rows back. But then I have multiple lambda predictions across all of those. And so what we decided to do is very consistent with dplyr and tidyr, is we give you a nested list of tibbles inside that. So you can see I'm still making predictions on 3 rows, but I have 80, it turns out for these data, I have 80 possible lambda values that would make predictions on. This might seem you're like, wow, that's complicated. It's way less complicated than what GlimNet gives you, and you'll just have to take my word for that. But if you were to look at, let's see, the first element of that, well, that's easy because they're all NA, because our first row of the original data set, we induce an NA value. But what you can see in that top part on the right is we have a value for the actual argument that you're getting predictions over, penalty in this case, and then .pred. Right? So if you look at the second element of that nested tibble, or that list column with tibbles in it, you can see that for different values of the penalty, I have the .pred. So I'm getting all those. And you can just use a simple tidyr unnest if you want to have a column that's penalty, row, original row number in pred, if you want to do some ggplots and things like that. So it's easy to unnest this data structure. But you'll always, again, start with the n you came in with. So one funny thing, funny story, we figured out in recipes and some of this, I'm really, you might not be surprised by this, I'm really big into resampling, right? And so a lot of times what we want to do is take the model that we have and feed it different variations of the original data to see what the variability is. And so when I was thinking about this, I was like, wow, we want people to specify the arguments to the model object before they run it, but we don't necessarily know what those arguments should be. So just as an example, random forest has mtry. And mtry should be on the units of the original number of predictors in the data, predictors in the data set. So if you have iris, mtry could be anywhere from 1 to 4. And that's pretty easy, right? But what happens when you're doing some fancy pre-processing method or with dummy variables, and you make dummy variables out of your factor predictors? You may not know what the number of columns you get are, but you need to specify mtry, so you don't, at the time where you have the data, you don't know what the size of the data will be when it actually goes to fit this model, okay? And since we delay execution of everything, you can't necessarily do anything, because if you remember, when I did my fit specification or my model specification, linear reg there doesn't, how would you parameterize that in terms of number of columns instead of the actual number? So we thought about this a lot and came up with this idea of what we call data descriptors. So at the time that parsnip actually evaluates the data set it's using on the model, like it fits the model, you have available to you some sort of like dummy functions. They work, but they don't work outside of any other context that capture different characteristics of your data set. So if you want to know like how many rows do I have, let's say your tuning parameter depends on the number of rows. Like let's say it's the number of nearest neighbors. Instead of you putting in a solid number that may or may not be consistent with, let's say, the resampled version of that, you can use .obs as a function. If you are going to convert, if you have any factor columns, .preds is the number of columns before in the data set before you make any indicator variables. And then I had to look because I don't use it that much. Like .cols is the number of predictors after you make dummy variables. So you can use these things as if they were functions when you specify your model. So just as an example, for random forest, I can say, let's fit a random forest. The ensemble has 1,000 trees, and I want mtry to be 3/4 of my columns, right? Whatever that number of columns ends up being. And so basically what happens is parsnip captures that as an expression, and then it only evaluates that expression right at the time you go to fit the model. So whatever that resolves to for that particular data set is what you'll get back. And so when you run that, you can see at the bottom, we haven't actually fit it yet. But when we run the translate statement, the mtry has that expression in it. It has not been evaluated yet, which it couldn't be because it's not the time it's going to be evaluated. When we go to fit, let's say we use empty cars. It turns out you can see the math checks out at the bottom. The number of predictors would be, I don't know how many it is, like 11 for this data set. But it's the number of columns minus 1, and then 75% of that is 7. And then you can see in the random forest output, it gets you 7 predictors. Okay, so it's a way to generalize what you're working on. And, knowing like a lot of the modeling stuff, we think we have all the descriptors in there for the possible things you might want to do. So if you want to downsample your data, if you have a big class imbalance, the random forest, for example, has a strata parameter. And you can say, hey, within this variable, sample this many at random, this many rows of the data that have that value. So if you stratify on your outcome data, you might say, well, let's say you have a data set with 100 data points and 90 of them are the majority class and 10% are the minority. You do want to have it randomly stratify the majority class down to the minority within each tree. That's what random forest would do. But again, if you don't know whether it should be 10 or 9 or 13 or whatnot, you can give it basically use those data descriptors to detect that at the time it goes to do predictions. Okay, so it seems kind of complicated, but it's pretty easy to do, at least in the code. If you were to try to execute .preds outside, like just in open code, it would say, yeah, no, you can't do that. Just like future plans, like what we're working on is, the main thing I'm working on right now is, if you have like a modeling package and you want to basically make that work with parsnip, we're writing an API where you can sort of like register your model with parsnip and have it work. Like you can always send us and people have like PRs if you want to include something. But let's say you're working on your dissertation and you'd like to use this infrastructure, but you don't want to publicize what your dissertation topic is. We're working that API that will let you do that. Case weights aren't implemented yet, so there's like placeholders, but it's not actually done yet. We also are coming up with like a pipeline type package. Like if you're on Twitter, like you could see, I've talked about this a few times. And a pipeline would basically integrate like a recipe, a parsnip model, and then maybe a post-processor that calibrates probabilities. From an earlier talk, there was a question about like having monotonic data. So in this workflow or this pipeline, you could add like a step in there that says, I need all my probabilities to be monotonically increasing. So the workflow object would take different things and would have its own fit function. So you don't have to call a recipe and do a bunch of stuff and then call parsnip and do a bunch of stuff. We'll like bundle all these actions together. And then just the last thing is, if you think about and people have well, how about adding this to parsnip or that? And just as an example, like a simple repeated measures model with just unordered replicates. You could fit that using like a non-Bayesian mixed model or hierarchical linear model or generalized estimating equations. So we kind of want to take sometimes like experimental designs and have those be parsnip methods so you can fit various types of models that kind of like different estimators of the same structural model. But it doesn't have to be like linear regression. It might be more geared towards the experimental design. So we definitely want to hear from people saying like, oh, have you thought about this, or how would you structure that? So please get in contact with us. And I think that is it.